We've looked at the resulting rolling moment. Now let's look at the resulting yawing moment. And to start that off, we need to look at what we mean by yawing moment. So if we look top down on a wing, a yawing moment is a moment that yaws the aircraft so that the right wing swings back. That's a positive yawing moment, by the way. So if you put your thumb out the bottom of the aircraft and then allow your fingers to curl around in the right-handed rule direction, then that is what we call a positive yawing moment. So this is any moment that yaws the aircraft to the left or to the right, and we call it a positive yawing moment if it moves the nose of the aircraft to the right. And we give it the symbol little n, like that, where, remember, rolling moment is little l, and yawing moment now is little n. So what we want to do is understand what the yawing moment is like, and this yawing moment is created by drag. Now let's draw our coordinate system on here. Remember, z, our aerodynamic coordinate system, goes out the left side of the wing. This is the front of the aircraft, and we're going to have drag acting in this direction along the wing, and that drag will be a function of span. So we'll call that d as a function of z. Okay, so the yawing moment, n, is equal to the integral from minus b halves to b halves, so across the entire wing, of z, that the location of that drag, times the drag itself, which is a function of z, dz. Okay, so we're going to integrate across there. And actually, in order to get the sign correct, we have to put a negative out front because positive drag here and positive z actually creates a negative rolling moment. So when that is positive and that is positive, we need a negative out front to match this sign convention where positive is swinging the nose to the right. Okay, so that's our yawing moment. Now we actually like to look at this in terms of non-dimensional yawing moment. So the way that we non-dimensionalize that is c sub n, little n, is the yawing moment divided by 1/2 rho v infinity squared times the wing area times the wing span. Okay, so that's how we're going to non-dimensionalize that. So we're going to plug this into this equation. But first, let's look at what d of z is. D, our drag, as a function of z. Now, for this inviscid solution, lifting line is inviscid. The only kind of drag that it can predict is called induced drag. You remember, when we looked at an airfoil, if we look at any location along this wing, the local angle of attack is going to be slightly different than the free stream angle of attack. Remember, we have a free stream coming in here, but the local angle of attack is affected. It's a summation of not only the free stream, but there's also induced velocity. Remember, we have this sheet of vorticity behind the wing, and that induces velocity along the lifting line here. And so at each location, the local angle of attack is slightly different because of that induced velocity. And that induced velocity is a function of location. Now, there's one other thing that can change our angle of attack at each location, and that is our rolling rate. So if we have some rolling rate p bar, then again our local angle of attack is a little bit different. So the drag now is simply a rotation of the lift vector by the induced angle of attack, and so it's our lift times actually the sine of our induced angle of attack, alpha sub I, plus zp over v infinity, which is the angle of attack that results from our rolling rate. So this is our change in angle of attack from the free stream. Basically, we take the sine of that, multiply it by the lift, and that's now the component of lift actually along the x-axis, which is in this. That's the x-axis there. it's in the x direction, okay? So we can use a small angle approximation and just knock out this sine term and just say it's alpha I plus zp over v infinity. And we know that lift is equal to rho v infinity times gamma of z. And we know gamma of z is a function of our capital A sub n values. So if we plug these each in now, so we're going to plug in gamma of z into there, we plug this lift into there, and then we plug this drag into there, and we then non-dimensionalize it according to this. I'm not going to work through the math. It's pretty involved actually, and again we get the integral of things like or of this infinite series over here, these a sub n terms, and also because of this alpha I term, this alpha I term also is an integral that we've discussed earlier. So that's another integral across the span. Anyway, the math gets a little bit nasty, but there are several terms that drop out because of the fact that we're still using this infinite Fourier sine series, and so that works in our favor. But the solution here for c sub n as a function of these capital A sub n terms then is pi times Ra over 4 times a summation from n equals 2 up to capital N of 2n minus 1 a sub n minus 1 times a sub n minus pi Ra times p bar over 8 times a sub 1 plus a sub 3. Okay, so this is our yawing moment coefficient as a function of these capital A sub n terms. And in the codes that I write, this is usually the equation that I use. I find it the most simple. You can split these out. You know, we know that capital A sub n is actually really a function of our little a sub n, little b sub n, cn, and dn terms. And you can split that out, but this equation gets more complicated when you do that. Another thing you can say is for a symmetric wing and symmetric washout, as we did before, a sub n and b sub n equals 0 for n even. But that doesn't simplify the solution very much. I still prefer just to compute my capital A sub n values and plug them in there. There is one thing, though, that sheds some light on what this C sub n looks like, and that is if we assume that we have a symmetric wing and it's using optimum washout. Okay, so it's using our optimum value for capital omega and little omega of theta, which we've talked about before. That's the washout that then creates an elliptic lift distribution on this wing in the absence of aileron deflection and rolling rate. If you do that, then actually you can show that C sub n can be written as Cn delta A times delta A plus Cn p bar times p bar, where Cn delta A is equal to 3 CL over 4 times little c2, and Cn p bar is equal to minus CL over 8 times 1 minus 6 d2. Okay, so again, just like we did with the rolling moment before, now the rolling moment before, this was a more general solution, but in this case we have to be using optimum washout along the wing. But if you do that, then you can write your yawing moment in terms of aileron deflection and p bar, where again Cn delta A is a controlled derivative. So for every deflection of delta A, we're going to get some ratio of that that gives us some value of Cn, and same with p bar. This is just some term that tells us that their yawing moment is directly proportional to p bar, just like it's directly proportional to delta A, and these are these proportionality coefficients or constants. Now, what you might notice is that these depend on C2 and D2, just like our rolling moment in our previous video depended only on C2 and D2 for a symmetric wing with symmetric washout, okay? So in that case, we can actually relate the yawing moment directly to the rolling moment and get rid of those C2s and D2s and write the yawing moment in terms of rolling moment. And what we get there is that Cn is equal to minus 3Cl over pi Ra times Cl, our rolling moment, minus Cl over 8 times p bar. Okay, so I'm going to box this, but this is still a rather specific solution. Again, this is technically only true when we're using optimum washout on a symmetric wing, okay? But what it does is it allows us to see a little bit more into this equation, because even though this general solution for the yawing moment here is much more complicated, it's actually dominated by terms that look like this, where we have something that's proportional to the rolling moment and something proportional to the rolling rate. So our yawing moment, you see here for this example, is directly proportional to rolling moment and rolling rate. And that proportionality constant in both cases depends on our lift coefficient. That proportionality constant grows with lift coefficient. And so we see that our yawing moment will be more pronounced at higher lift coefficients, which generally correspond to lower speeds. Okay, for a given weight, if we slow down, that means we are operating at a higher lift coefficient, and so we'll get a stronger yawing moment at the same rolling moment or rolling rate than we would at a higher speed or a lower lift coefficient. Another thing that we see here is that the sign of the yawing moment is opposite to the sign of the rolling moment, and also opposite to the rolling rate. And that's actually a very important thing, that the fact that usually our yawing moment has an opposite sign of our rolling moment, that's called adverse yaw. When we get into aircraft dynamics, we'll talk more about that and the why that's so important. And many times there you actually want to you would prefer to have proverse yaw instead of adverse yaw, where your rolling moment and yawing moment have the same sign or are not correlated. So you can create a rolling moment without producing a yawing moment. But in general, most wings will create a yawing moment that has an opposite sign to the rolling moment, and that is called adverse yaw. So that's a very common condition. Most aircraft deal with it, and we'll talk more about that when we get into aircraft dynamics.